we're looking at question 16, October 2021. This question is about magnesium, and even it's about one element and different topics weaved into this element. Metallic bonding, we'll be looking at ionization energy, we'll be looking at enthalpy change of solution of a magnesium compound as well in this question. First question is, first part, it's asking magnesium has metallic bonding and is a good diagram. Labeled. Many times I see students not labeling their diagrams. The metallic bonding in magnesium, and explain why it conducts electricity. Why it conducts electricity. Include correct charges. They don't normally say this for a type of element like this. So that's a big hint there. You see magnesium is in group 2, and being in group 2, it's going to have, it's got 2 electrons in the outer shell. That means those 2 electrons are delocalized. So the charge of the ion is going to be 2+. You can show it. The mark scheme requires a minimum of 2 rows. Minimum, it must have at least 2 rows. So let's just stick to 2 rows. And you've got your delocalized electrons. For what I've just drawn now, you'll get 1 mark out of 3 so far. Let's label. Of Mg2+. You've got here your delocalized electrons. And why does magnesium conduct electricity? Because the delocalized electrons can move or are mobile, which means the same thing. 3 marks. Moving on. This is the successive ionization energies for magnesium. You've got this successive means one after the other. Magnesium is in group 2. It's got an atomic number of 12. These are all of them. All ionization energies. Successive ionization energies. Let's have a look at the question. Write an equation to represent the 4th ionization energy of magnesium. You see, whichever, whether it's the 3rd, 4th, 5th, whichever type of ionization energy is, that's the ion that's forming. So in this case, it's the 4+ ion. And 1 electron is removed because it's successive. That means it must be forming from an Mg3+ ion. And ionization energies are always in the gaseous state. Yeah, state symbols are essential. You don't need to write state symbols for electrons, but for the ions you definitely do. It says here, explain how the successive ionization energies provide evidence that magnesium is a group 2 of the periodic table. Why is it in group 2? Let's have a look at the values. Ladies and gentlemen, can you see that you're removing the first electron is that many kilojoules per mole, losing the second electron is that many kilojoules per mole. It's going up by about 700. And then suddenly there's a massive jump to 7,000, so 6,000 jump, 3,000 jump, 3,000 jump, and so on. So it's just asking this change, this large increase or large difference or a big jump represents the electron being removed from a different shell. So what do we say? Just one marker here. That the fact that there is a big jump, or we could say large difference between the second and third ionizations. One mark. Next question. You see, it says in table 6.2, below the add a tick below the stations that are responsible for removing an electron from a full orbital in a magnesium atom. Before we do this, you see we've got 1s2, you got 2s2, you've got 2p6, which will cover these 6 electrons here. And then you've got a 3s2. If we just draw these out, these orbitals. And the electrons that you have, you've got 1, 2, 3, 4, 5, 6, 7. Look how I'm filling it up. Like passengers on the bus. They don't want to sit next to anyone, so they occupy the seats in a single manner, and only then they double up. And then you've got your last 2. 1, 2. I will use a grey pen to dull it out. So what we got, what you're doing, you're removing the first ionization energy. You are removing an electron from a filled orbital. Once you remove them, then you again are removing an electron from a full orbital. Then you're removing again an electron from a full orbital, again from a full orbital. Then you're not, which is these 3 remaining. And then you are removing again this one here, then you're not, and then you're removing it again, and then you're not. So you don't need to put crosses in, but these are the ticks that you'd give. Moving on. This question is about the enthalpy change of solution for magnesium fluoride. Can be determined indirectly using an energy cycle based on the enthalpies below. What enthalpies do we have? We've got lattice enthalpy. We've got hydration enthalpy of both the ions. What is meant by the term enthalpy change of solution? Enthalpy change of solution, these definitions always refer to 1 mole. It's the enthalpy change when 1 mole of a substance dissolves. To form an aqueous solution. This is the main wording. 1 mole of a substance dissolves. Moving on. On the dotted lines, add the species present. You see, if we look over here, you've got gaseous ions. And gaseous ions, when they react together, they're going to form the ionic solid. This ionic solid, this change from there to there is going to be your lattice enthalpy. Let's call that Le. Oh, I didn't realize it's the other side already. Oops, I didn't see that. Let's rub this off. It's already done. Lattice enthalpy is already done there. So from, yep, that's your lattice enthalpy. Didn't see that. If that's your lattice enthalpy, and what you've got here, you've got a solid that we're going to dissolve in a solution, and that's going to give you aqueous ions. This must be your enthalpy change of solution. This will give you Mg 2 plus, which is aqueous, and 2 fluoride ions, which is also aqueous. Now, what that leaves us with, you've got two changes that we need to, these changes over here, from there to there and there to there, these are going to be your hydration enthalpies of magnesium ion and fluoride ions. So all we do, we need to pay careful attention to the state symbols. Let's do, actually, which one is more, has a greater magnitude? Looks like magnesium. It doesn't really matter. This is not to scale. Let's just do magnesium first. Mg2 plus, and this becomes aqueous. Can you see, ladies and gentlemen, from gaseous, it's gone to aqueous. And then the fluoride ions stay the same. They are the gaseous state. And then you are going from gaseous to aqueous. And that's the enthalpy change of hydration of fluoride ions. It is then asking, calculate the enthalpy change of solution. Ladies and gentlemen, what we're trying to do is work out from there to there. That's what we're trying to do. But we don't know what that is. So we're going to go use Hess's law. This is our starting point. And this here is our end point. This route, we don't know what it is. So we're going to go the other route. We're going to go against this arrow. We are going to go with this arrow and with this arrow. That means the enthalpy change of solution is equal to the enthalpy change of hydration minus the enthalpy change of lattice enthalpy. That will be our formula, so to speak. So what is this? Let's add up the hydration enthalpies. Remember, these are per mole. And for the fluoride ions, we've got two of these. So this will be hydration enthalpy of magnesium is minus 1920 minus open brackets Mark scheme is doing it in a different way. Let's just try this way out first. So we got minus 120. Hold on a minute. Enthalpy change of hydration, magnesium. Yep. And let's, we need to add plus the enthalpy change of hydration of fluoride ions, which is minus 506 times 2. So that's going to be your enthalpy change of hydration. And then we minus the lattice enthalpy, which is minus 2926. Minus 2926. Please be mindful of arrows, signs, negatives, positives. We'll see what this says. Minus 1920 plus, open bracket, minus times 2, minus, open bracket, minus again, 2926, close the bracket, and the answer is minus 6. And the mark scheme supports that. In the mark scheme, they showed this the other way around. That's why I got a bit worried. Last question, the enthalpy change of solution of magnesium halide shows from MgF2 and MgI2. Explain why it is difficult to predict whether the enthalpy change of solution becomes more exothermic or less exothermic down the group. So because magnesium ions stays the same, we're not really comparing magnesium. We are comparing, it's a case of fluorine versus iodine. And you can see that the fluoride ion and iodide ion, so that versus that. Now what it is, you always discuss these types of questions, you always discuss the charge, you always discuss the size. Because the charge is the same, in this instance, you wouldn't discuss it. There's no need for it. But so we can say that the iodide ion has a greater ionic radius. Because it has a greater ionic radius, its charge density will actually be less. So I minus has a greater ionic radius, so its charge density will be less. Charge density, that same -1 charge is spread over a larger volume. Charge density is smaller. As a result, the lattice enthalpy will be less exothermic. Ladies and gentlemen, whenever you're referring to lattice enthalpy and the effect of these changes, always say, is it less exothermic or will it be more exothermic? These are the terms that you want to use. Don't say it's more positive or more negative. You need to say, is it less or more exothermic? That's the terminology used. In this instance, iodide ion to magnesium ion is going to be that that reaction, that lattice enthalpy will be less exothermic. Now the thing is, with hydration enthalpy, so if you've got the attraction between iodide ions with the water molecules, because the charge density is lower, the enthalpy change of hydration, enthalpy change of hydration for minus will also be less exothermic. Okay, now the thing is, if you look at let's go back to the cycle. So if the hydration, so here it's a let's look at this formula. If we're saying that the enthalpy change of hydration will become what do you say? It becomes less exothermic, and lattice enthalpy also becomes less exothermic. We don't know. It's difficult to predict what is the change in this. Actually, would it be helpful if we compare? So we're trying to compare this, the effect on this, versus the effect on this. How can I explain this point to help you understand? let's try to look at the numbers. You see, these are the hydration enthalpies. Now, if the hydration enthalpies are going to be less negative in the case for iodide ions, and the lattice enthalpy is also going to be less negative. Sorry, I'm using the wrong words here. Bear with me. Less exothermic, and lattice enthalpy is also less exothermic. You see, we don't know the extent or the magnitude. Magnitude meaning, take away the charges. We don't know if the magnitude is going to be less or more than the magnitude of the hydration enthalpy. So as a result, we don't know, it's difficult to predict because there's two variables. I don't think I've explained that term properly, but any suggestions, please do let me know in the comments. But what the mark scheme says, it says it's difficult. I've seen questions like this before, actually. Difficult to predict whether lattice enthalpy or hydration enthalpy has a effect. I'm not happy with this last point in the comments, with this last point. Help me understand this point better. With that, I think that's the question. I'll see you tomorrow.